Oh, good old limits. This first one is going to infinity. So when you're thinking about a graph, the x-axis going to infinity, you got to think about, okay, what is this graph trending towards? So let me show you guys a quick example right here. If you had a graph going like this looks like a rational function. What is this graph trending towards as you're going towards infinity? It's trending towards this horizontal asymptote. And so what you can do, without having to do any kind of calculus, you can just look at your rational expression and do one of your algebra tricks to figure out what is the horizontal asymptote. So what you do is you look at the degrees. The degree of the top function and the degree, well, the top polynomial and the degree of the bottom polynomial. The bottom polynomial has a degree of 5. It's the highest exponent. The top one has a degree of 4. When that happens, you know that the horizontal asymptote is y equals 0. So that means this rational expression has a horizontal asymptote at 0, which is going to be our answer for this limit. That is the y value that the function is trending towards as we go towards infinity. There's a couple other scenarios, and that's if the degree on the top is equal to degree on the bottom. If that's the case, then you just take the leading coefficients, which would be 3 and -8, and you would divide those to find your horizontal asymptote. If your degree on the top is greater than the degree on the denominator, in that case, you have a slant asymptote, something that kind of looks like this, and the function would be trending towards positive infinity. Remember, answers to limits are y values, and so that's what you're looking for. You're looking for y values. All right, let's look at this next one. The next one says, what is the y value as you get closer and closer to 0 from the left? That's what that little negative means right there. So this function right here should be a recognizable function. It looks something like this. All right, now 0 is right there at the origin. As we're going across the x-axis, getting closer and closer to 0, what is this line trending towards? So in this scenario, it's really important to denote which infinity we are going towards, because the function is going downwards, and so that one's negative infinity. It is arguable to say that the limit does not exist, but in this case, negative infinity is more correct than does not exist. Now for the next one, the first thing you want to do is you want to just plug in the 1/3 to see what happens. When I plug in 1/3 on the top, I get 9 times 1 over 9 minus 1. And on the bottom, I get 3 times 1/3 minus 1. On the top, 9 times 1 over 9 is 1, so you have 1 minus 1. On the bottom, you end up getting the same thing. So we end up getting 0 divided by 0. 0 divided by 0 is an indeterminate form, so that means you have to do something else to figure out the answer to this problem. So the next step, the next thing that you can do for a problem like this is you try to algebraically manipulate the problem to see if you can simplify anything and then try substitution again. So on the top it says 9x squared minus 1. On the bottom it says 3x minus 1. And then hopefully you recognize at the top is a difference of squares. And so we can factor that to say 3x minus 1 times 3x plus 1. And that's being divided by 3x minus 1. And so we can cross out 3x minus 1. And so in this case, it appears that our function has a hole in it. Now this is just a linear function, but the actual function is this. And this function, you're not allowed to plug in 1/3. And the reason why is because if you plug in 1/3, the denominator equals 0. Which means we're not allowed to plug in 1/3 to this. So the question is, what would this line be trending towards when you're approaching 1/3? So that function will look something like this guy right here. We have a y-intercept right here at 1, and then we're going up 3 right 1, so it looks something like this. And our question is, if we were approaching 1/3, that's a 3 right there, what is that number? That's actually supposed to be a hole right there. Let's put a hole right there. There you go. So in order to find out what that y value is right there, what we're going to do is just simply plug in 1/3 into this and see what we get. So 3 times 1/3 plus 1. This would equal 3 over 3, which is just a 1, so we get 2. And that is our answer for this one. So we're approaching 2. This next problem reminds us to always try to substitute first before trying to simplify. You can simplify this one. The top factors and the bottom factors. The top one is a difference of cubes, and the bottom, the x squared minus 4, is a difference of squares. And that would simplify. I'm not sure. I think you would get the same answer no matter which way you do it. But if you just simplify, substitute this in, you're going to get 0 minus 8 and 0 minus 4. When you divide negative 8 and negative 4, you're going to get positive 2. And that is your answer for this one. All right, next one. This question is trying to see if you understand that when you're approaching infinity, you're approaching your horizontal asymptote. And so it's saying in order for y equals a to be a horizontal asymptote, which of these has to be true? Now let's think about that for a second. If y equals a is a horizontal asymptote, that means, I don't know where a is, I'm just going to put it right here in the positive spot. If that's a horizontal asymptote, that means as we approach positive infinity or as we approach negative infinity on the x-axis, we are approaching this y value. So, which one of these would make sense? This one doesn't make sense. We have to be approaching to some kind of infinity. So it's going to be either C, D, or E. If this one says as the x approaches positive infinity, h becomes infinity. That's not what we want. We want it to be approaching this a. And actually now when we look at it, only this one is approaching a as we're going towards one of the infinities, either negative infinity or positive infinity. So our answer is D. And now we have a scary piecewise function. I know some of you guys flip out when you see this, but don't flip out. It's just talking. This is saying that there's 3 different parts to the function. There's this rule, and this rule, and these are the qualifications for each of those rules. So if x was greater than 2, then you have to follow this rule right there. So it says it's not continuous. So this function g is not continuous at 2y. And in your head, you should be thinking, well, it's either not continuous because we have a hole at 2. We have jump discontinuity. That should be an open dot. Or we have an asymptote at 2. Right at 2. So it'd be something like this. Okay, so what's happening there? Most likely it's not an asymptote because I see 2 linear rules. That's a linear rule and that's a linear rule. And then this is a 5. I totally forgot about the removable discontinuity, which is kind of like the hole. That just means that there's like a dot right there off to the side. And so what if this is what's happening to our line and this is a 5 right there? That's a removable discontinuity. All right, so let's read our answer choices. This says g of 2 is not defined. Now this is not true because if you do plug in a 2 in there, it says when x equals 2, we get negative 5. Therefore, it is defined. So A is definitely not going to be a right answer, which also eliminates E, which is all the above. The next one says, as G approaches 2, G does not exist. Okay, so this does not exist. The limit of G does not exist. Now, in order for a limit not to exist, the left and the right hand limits have to not equal the same y value. So see my example right here, the jump discontinuity. If I come from the left, the function is going to be approaching, let's say, a right there. If I come from the right, the function, which is this guy, is approaching b right here. So because the left and the right hand limits do not equal each other, the limit does not exist. So we would have to have a jump discontinuity for b to be true. So that one can be true, but let's look at the other ones to see if those ones can be true. The limit of g as we approach 2 does not equal g of 2. Okay, now this right here is a removable discontinuity. In this case, the limit does exist at 2 because the left hand and the right hand limits are approaching the same y value. They're not approaching 5, but they are approaching whatever this value is right here. Let's call that value a. So that means the limit does exist. But in this case, in this scenario right here, g of 2 would equal 5, because if I plug in 2, I get 5. And then, but the limit would equal a. The limit of g of 2, which would look like this, the limit as x approaches 2 of g would equal a. So in this case, g of 2 does not equal the limit as we approach 2. So does that make it discontinuous? Yes, which means that C is a potentially right answer as well. Okay, let's look at the last one. G of 2 does not equal -5. That's just a weird statement. That's just like saying, hey, do you know how to read this function? Oh, that's not true. G of 2 is -5. It's what it says right here. If you plug in 2 into G, it does equal -5. So it's kind of silly. So we just have to determine if B or C is correct. Now the thing is, both of these, B and C, can be a statement for why G is not continuous. So what we're going to have to do is we're going to have to actually graph this to see what we have, which might be something you try to do in the first place. But I was trying to do it the fast way. And I am going slower because I'm explaining this. But anyways, so let's graph this really fast. If we're greater than 2, we're going to be following this rule right here, which has a slope of 1 over 1, and we're starting down here at -3. Actually, I don't care about -3. -3 is its y-intercept if it got down there, but we're just concerned about the x values that are greater than 2. So let's plug in 2 to that. If we plug in 2 to x minus 3, we would get -1. And we're not existing there, so I'm going to put an open dot right there. And then from that point right there, I'm going to go up 1, right 1, up 1, right 1, up 1, right 1, whatever. It doesn't have to be perfect. And then at 2, we equal -5. So -5 is going to be down here, which is not, see how they're discontinuous right there? It's kind of looking like this one right now. And then 3x minus 7, what is that going to look like? So if we plug in 2, we would get, see, that would be a 6. 6 minus 7 would be -1. And so we would be right back here. And then something else will happen. So it's a positive slope, but it's a really steep slope. So it looks something probably like this, but it's going to connect to that open dot. All right, so looks like we have a removable discontinuity. So does the limit not exist? Nope, the limit does exist. The limit for this case equals -1 because the left and the right are both approaching the y value -1. So that means C has to be our answer. Sorry for the long drawn-out explanation on that one. Finally, last one on this page, we have 319. I'm going to plug in 0 first to see what we get. So we'll have 3 times 0 squared plus 2 times 0, which is just going to be 0 on the top. And in the bottom, we have 2 times 0 plus 1. So the top gives us 0, the bottom gives us 1. 0 divided by 1, you are allowed to do that, so our answer is 0. So plugging in works for that.